Chapter 16 covers the concepts of electric potential energy, and capacitance. We start with electric potential energy. It's given by the equation at the center of the screen, which says UE, that's electric potential energy, is equal to charge multiplied by the electric field multiplied by the distance that it travels. In this case, on the diagrams at the bottom here, on the left we see a charge that's placed inside of an electric field between two plates. Right now, this positive charge is sitting against the negative plate, which is where it wants to be. It doesn't want to move away from this spot because the positive and negative are attracted to one another. However, if I were to take this positive charge and put work in, I could lift it away from the negative and towards the positive. In doing this, I would be giving it potential energy because now as soon as I let go of this charge, it will begin to move, rather rapidly, away from the positive and towards the negative. If you look on the right, we see the analogy with Chapter 5's concept of gravitational potential energy, where we have a mass against the Earth, and when we take that mass and we lift it away from the Earth, we give it potential energy. And in much the same way, as soon as you let go of it, that mass will fall back towards the Earth. In the case of Chapter 5, we use the equation U equals mgy, and we're really using the same concept here, except we're replacing mass with charge, because charge is what dictates how much electric force there is. Instead of gravity, it's the electric field that really determines the direction and the strength of the falling. And instead of y, which was limited to really vertical movement, we just more generally call it d for distance. It doesn't matter whether it's up, down, left, right. In any case, it's the same really for an electric charge, no matter how it moves, as long as it's moving from an area of high electric potential energy to an area of low electric potential energy. However, we don't always want to talk about electric potential energy because in this chapter and the following chapters, we're going to be talking about kind of bigger scale. We're going to talk about electric circuits where you might have a battery hooked up and many thousands or millions or billions of electrons moving through that circuit, and you don't really have the time or the interest in worrying about the exact amount of charge that's moving. And so one concept and one quantity that we get is something called the electric potential difference. And it's represented by this symbol here, delta V, which is the change in electric potential. And it is calculated using the equation change in electric potential energy divided by charge. So basically we're pulling charge out of the equation so that we don't have to worry again about the exact amount of charge. When we do this, we're left with a unit that we call the volt. And that's named for a gentleman, Count Alessandro Giuseppe Antonio Anastasio Girolamo Umberto Volta, who was an Italian physicist who worked on electricity and batteries. He's actually known for inventing the very first functional battery, and therefore has earned the honorary unit of volts. When we look back at that equation, we can see how when we divide charge out of electric potential energy, the charge cancels, leaving us just with the strength of the electric field and the distance between the 2 points that the charge has been moving through. And in this way, now we can talk about just more generally volts without worrying about the specific number of electrons or charges moving. And this lets us compare, let's say, a 9-volt battery to a 1.5-volt AA battery. And we can learn about the difference in those and what they're able to accomplish in a circuit. One thing that's important to note about the electric potential difference is the difference. We are always talking about a difference in the exact amount of electric potential from point A to point B. We don't really care about the specific amount at point A and point B, but again, it's how much it changes by. And so this diagram shows us an example where we start with point A, and let's say it has 100 volts of electric potential at this point. If we were to move that charge to a place where now it has 300 volts of electric potential, we'd notice a difference of positive 200 volts. In the second example, let's say that at point A it had 1100 volts, and when we moved it to point B, now we have 1300 volts. Still a change of 200 volts. In both cases, since the change is the same, really the functionality is the same as well. We don't really care about how much specific electric potential it has, because the work or the accomplishment comes from how much it changed by. Some important points help us to kind of resolve just how we talk about electric potential. Very similar to the electric field, which we drew lines for that represented what would happen to a positive charge, electric potential is defined by what would happen to a positive as well. And therefore, positive charges, when released, will move always from an area of high electric potential to an area of low electric potential. And likewise, a negative, when released, will move from an area of low potential to an area with high potential. So just opposite of the positive. Looking at this, what we see then is if this is our positive, then as we get closer and closer to this positive, we're going to have higher and higher potential. Or as you get further and further away from it, you'll have lower and lower potential. And therefore, in this example, using this new equation, what this equation lets us do is calculate the exact amount of potential difference from any 2 points. So if we started at point A, and then we were to move to point B, we should have some sort of increase in the amount of electric potential because we've gotten closer to this positive charge. The equation can be used in the way where we have K, which is our constant from chapter 15. It's 9 times 10 to the 9th. Q would be whatever the charge is that's producing this electric field, and then R is your distance from it. So in finding the change in electric potential, you're going to first use your R, your final R, this B point, and then you'll subtract from that the same quantity but using your initial distance from R. And what that means is because RB is going to be smaller than RA, you're going to end up with a positive change. And again, that makes sense because we're moving closer to a positive. We're moving closer to a point of higher potential. Just to wrap that up, electric potential therefore increases anytime you're getting closer to a positive source, and it decreases as you're moving away from a positive source or towards a negative source.